started the recording, and let me share my screen now. Okay, I hope my screen is visible. Is it visible?
No, sir.
No, sir. Not yet, sir.
Okay. Okay, I think it's visible now.
Yes, sir.
Yes, sir.
Okay. Good.
Hello, sir.
Follow.
Sir, there is a continuous background noise.
Yes, there is some construction work going on over there, so
Okay.
I cannot hear.
Okay, sir. No problem.
Uh, Good. So let us begin our discussion. Uh, well, now this is the first time in this semester that we are meeting, right? Okay, and well, now this particular topic is from your first semester. Somehow it was left behind. So before we begin our new semester, we thought that we would cover up these things as well, so that you won't lose anything, right? So I am going to talk about two multiple sequence alignment algorithm called one of them would be T coffee and another one would be D align. Okay, so let us begin. You might have learned so far, whatever multiple sequence algorithm that you might have learned, well, they can be categorized into one of the group of multiple sequence alignment called as progressive strategy. Well, say for example, your cluster and muscle, they work by progressive strategies for performing your multiple sequence alignment. Okay, now the general strategy for aligning multiple sequences can be outlined basically as well. Say for example, you would start out with a pair of sequence. Okay, starting with a pair of sequence, and you would select a pair of sequence out of multiple sequences and then align them, and subsequently you would go on adding up the subsequent sequences in order to generate a multiple sequence alignment. Okay, so since you are progressively adding either sequences or profiles to the previously aligned sequences or profiles, we call such a type of strategy as progressive strategy. Okay, so now these progressive alignments are a typical example of heuristic algorithm. Okay, and you can more precisely say that they belong to greedy algorithms. Okay, so now what are heuristic algorithm? Okay, so heuristic, you can call it as an approach to a solution by trial and error. Well, say for example, in this case you have multiple sequences. When you start out with well, say for example, aligning first sequence with another sequence, then first sequence with third sequence, or second sequence and third, or third and fourth, or fourth and first. Okay, so what you do is that you trying to find out a solution for any given problem by trial and error method. We call such a methodology as heuristic approach of finding a solution. Okay, and multiple sequence alignment also does the same thing. Okay, so now talking about what are greedy algorithm, you can consider this greedy algorithm as the methodology in which you decompose the problem into small pieces. Okay, and then choose the best solution to each small piece without paying attention to the problem as a whole. Okay, so what I mean over here is that, well, say for example, you have been provided with these few sequences, well, say for example, and now your big problem is to find out the multiple sequence alignment of these sequences. Okay, so now what you do is that you would decompose your bigger problem into smaller problem. Like we would decompose this problem of solving multiple sequence alignment of all of these sequences into smaller problems, like solving doing pairwise alignment of sequence 1 and 2 separately, then do pairwise alignment of 3 and 4 separately. Okay, and when you perform this pairwise sequence alignment, which is eventually a part of this bigger problem, when you try to find out solution for a smaller part, you will not pay attention on the fact that it is going to be solution of a bigger problem. You try to find out the best solution for a smaller problem that you are dealing with by hand. Okay, so such a type of methodology, or such a type of algorithms are included in greedy algorithms. Okay, so your in case of, that is what I already told you, in case of multiple sequence alignment, the overall problem of alignment of many sequence is decomposed into series of pairwise alignment step. Okay, now as progressive alignment are heuristic. Okay, and heuristic methods का सबसे बड़ा ड्रॉबैक ये होता है कि they don't guarantee the best possible alignment, या what we call it as an optimal alignment. Okay, there can be multiple solution if you try to opt for such heuristic method. Okay, so whatever progressive alignment methods that are being implemented so far, or that has been proposed so far, you can kind of distinguish between these different methods on several ways. Well, say for example, your progressive alignment method can differ in the way they choose the initial pair. Okay, well, say for example, you have got these multiple sequences that are needed to be aligned. Well, say some alignment method, or say some progressive alignment method might select first two sequences, or they might have some different criteria for selecting the initial pair. Okay, so they differ in how they choose the initial pair, and then how do they subsequently align the remaining sequences. Okay, so now if a program they can differ in a way that if the progressive alignment program aligns every subsequent sequence to the single alignment. Well, say for example, some of the progressive alignment method, they align the first two sequence, then add the third sequence, then add the fourth sequence, so on and so forth. Okay, or they can also do like well, say for example, if there are these sequences, separately these two sequences would be aligned first, separately these two sequences would be aligned first, this would be added to this alignment later, this sequence would be added to this alignment later, and eventually whatever the groups of alignment that are formed, they can be aligned together. Okay, so that is what it means. Whether the program aligns every subsequent sequence to a single alignment, or it creates subfamilies like this. These three sequences would be aligned in one family, and these three sequences would be aligned in another family, and then the separately aligned families can be aligned together later on. Okay, so these are the different ways in which your progressive alignment methods can differ. Okay, another way around is that these progressive alignment methods differ in the way they score individual alignments. Okay, or the alignment of individual sequence to previous alignment. So the scoring criteria can also be somehow different. So these are the ways one can distinguish these methodologies. Okay, so now you people are already aware of what are the steps that are involved in multiple sequence alignment by Clustal. Okay, so what do you do in Clustal? You begin with well, say for example, multiple sequences. Then what you create is something called as the distance matrix. Okay, so based on these values in this distance matrix, you create a dendrogram, okay, or something called as the guide tree. Okay, and you begin alignment of most closely related sequence pair in the guide tree using dynamic programming, and progressively you can add up the remaining pairs or remaining sequences into the alignment. Okay, or what you can do is that you usually create profiles if two sequences are separately aligned, and then you can end up aligning those profiles as well. Okay, so these are the basic 5 steps that are involved in your cluster. So this is just a brief explanation. I don't want to go in more details of this since it has been already covered. Okay, so what happens is that first, after creating the distance matrix, you use the results of these distance matrix to create something called as the guide tree. Okay, so now the objective of this guide tree is to help the computer program to determine of the given multiple sequences which are the two that are needed to be aligned first and what should be the subsequent alignment order. Okay, so in this way this guide tree, or some people also refer it to as a dendrogram, it has got no phylogenetic meaning. Okay, so it cannot be used to show the evolutionary relationship among these sequences as such. Okay, so these are only used as a reference just to decide what should be the order of sequences that is to be followed while aligning those sequences. Okay, good. So, well, say for example, this is a typical guide tree that you might end up using. That you might end up using Plustal. Okay, and these guide tree would help you figure out in what order sequences are needed to be aligned. Okay, well, say for example, in this guide tree you can see this A and B are most closely held together, E and F are most closely held together, I and J are present very close to each other in your guide tree. So in this way you would first align these closely related sequences from the guide tree first, then the next neighbor of this A and B alignment would be C. You can end up adding your C to already align A and B. In this way, you have created something called as a profile. Okay, what we are doing here, when we subsequently add D to our previous alignment of A, B and C sequences, we say that we have created a profile of A, B, C, D. And eventually at the end, what you do is that you end up aligning these profiles, or the remaining sequences can also be added to your multiple sequence alignment. So this is, a general strategy for that is used for aligning the sequences using progressive strategies like cluster. Okay, so now let us discuss what are the factors that affect the quality of multiple sequence alignment. The first and foremost factor would be the scoring matrix that you use for aligning the sequences. Okay, second factor would be gap penalties. You are already aware of what is gap opening penalty and gap extension penalty. What gap opening penalty you set and what gap extension penalty you set would eventually determine the quality of your assignment. Okay, and in multiple sequence alignment there is another parameter called as weighing parameter. Okay, so these weighing parameters are used in deciding the scoring matrix for sequence profile alignment and profile alignment. ओके, तो मल्टीपल सीक्वेंस अलाइनमेंट की प्रोसीजर में when you end up at the level where you need to align the sequence to previously created profile, or if you want to align two profiles, you would have to select some different scoring metrics. So these weighing parameters eventually help in determining what kind of scoring matrices are to be used in such scenario. Okay, so now let us talk about some practical consideration, like when are you supposed to use the cluster. Okay, so your cluster can be used to align any group of protein or nucleic acid sequences that are related to each other over their entire length. Okay, well, say for example, you can align these three sequences as I am showing over here, when you know that all of the three sequences are related to each other from end to end. Okay, it should not happen that it contains one domain over here, okay, and that domain is not present in the remaining sequences. It should not be like this. Okay, the basic criteria is you should use cluster only when you know that these whatever sequences that you are trying to align, well, all of these three sequences are related throughout their length. Okay, second criteria is that cluster is optimized to align the set of sequences that are entirely collinear. Okay, collinear यानी क्या? That is, the sequence have same domains in the same order. You know, well, so for example, if you end up aligning protein sequence and now you know that proteins are modular entities that can have different domains. So this can be domain 1, this can be domain 2, and this can be domain 3. Okay, so now it is advised that when you use cluster, that the same three domain are present in the same order in all of these three sequences or whatever sequences that you are dealing with. It should not happen कि your domain 3 is present over here and you end up having domain 1 here and domain 2 here. In such case, things would go wrong. You cannot use cluster. Why? Because somehow cluster uses your global alignment for performing those pairwise sequence comparison. Okay, and global alignment may it becomes very difficult to detect and align the local similarities. Okay, so this is one of the practical aspect of using cluster. So if your sequences follow these two criteria, then go proceed on using cluster. Okay, so now let us talk about what are problems with your progressive strategy that is used by cluster. Okay, so one might ask, does the quality of my guide tree matter? Okay, because we are going to we would the cluster has created that guide tree which eventually decide in what order sequences are needed to be aligned. Okay, and it uses some clustering algorithm like neighbor joining that creates those guide tree. So the answer to this question might be ki, usually the quality of guide tree, if you choose to align closely related sequence, it would definitely cluster them quite well. Okay, so you don't have to worry if you don't have to worry about the quality of the guide tree if you select to align the sequences that are very closely related to each other. But if you end up comparing the sequence which you know are distantly related, then you would have to be very peculiar about deciding the quality of your guide tree. Okay, then your cluster is supposed to have something called a single parameter problem. Okay, so now consider this scenario. What you are doing is that you are using one weight matrix and one set of penalties for all of the sequences. Well, say for example, just I'm giving an example that you are trying to perform this multiple sequence alignment of these 4 or 5 sequences. Okay, and what you do is that you use one weight matrix, and once if you use one weight matrix and a single set of penalties for all of the sequence, then whatever the best set of parameter for one part of alignment may not be the best for another part. Like, well, say for example, of these multiple sequences, well, it might happen that sequence number 1 is more similar to sequence number 2 as compared to sequence number 3. Okay, while sequence number 3 might be more similar to sequence number 4 and compared to sequence number 5. Well, say it can happen that way, right? In your multiple sequences that you are dealing with, some of the sequences can be related or can be similar, while some of the sequences can be divergent, or you can say the similarity or identity might decrease. Okay, so now what if you use a single weighing matrix and a single set of penalties for aligning all of the sequences? Then it might become problematic. Why? Because whatever set of penalties that you are using for aligning these two sequences may not be optimal for aligning the remaining two sequences as such. Okay, you might require another set of penalties and weighing matrix to deal with this problem. Okay, so now we'll say, for example, this is something called a single parameter problem. Okay, so in protein sequence alignment, different scoring matrices are used for each alignment based on what might be the expected evolutionary distance between these sequences. Okay, so well, say for example, in other words, in your multiple sequence alignment, okay, if two sequences are very close to each other, they are very close in your neighbor joining, well, whatever guide tree that you have created. Okay, so if they are very, these two sequences are very close to each other in your guide tree, a scoring matrix that is optimized for aligning the two sequences that are closely related to each other, that particular scoring matrix should be used. On the other hand, if you are trying to align the sequences that are distantly related to each other, some different scoring matrix might be optimal to be used. Okay, so well, so for example, if these two sequences A and B are close to each other in your guide tree, then you might use this blossom 62 for aligning this closely related sequence. While if you want to end up on aligning this sequence B with some far distantly related sequence in your guide tree, we'll say for example a sequence D over here. Now you know that expected evolutionary distance between this sequence B and D is high. Therefore, you might use some other scoring matrix like Blossom 45 that is optimized for aligning distantly related sequences as such. Okay, so you eventually your program need to decide what to use when, what kind of scoring matrix is supposed to be used when, and what weighing parameters are supposed to be used when. Okay, so and it becomes a difficult business when you try to align these sequences. Okay, the next problem that these progressive alignment strategies face is something called as the local minimum problem. Okay, so what we call it as local minimum problem is nothing that, you know, we'll say for example, you have aligned the first two sequence. Okay, then you added progressively third sequence, then you progressively added your fourth sequence to the alignment. So if something went wrong in the initial stages of alignment, that somehow cannot be corrected, or the problem cannot be rectified in the subsequent steps. Okay, it would be carried on to the subsequent stages of your multiple sequence alignment or the subsequent procedure. Okay, that is what we call as the local minimum problem, which states that if the initial alignment have a problem, it cannot be removed. They can't be removed during subsequent steps. It would be carried out as it is, and sometimes it happens that problem can be amplified during the subsequent stages. Okay, that is called as local minimum problem. Okay, now when not to use cluster, right? When you are sure that sequence do not share common ancestry, that is the time when you decide कि आपको cluster use नहीं करना है. Okay, when sequences have very large n and c terminal overhangs, that is when sequences are not of similar length, you are not supposed to have you are not supposed to use cluster in such scenario. If you know that sequences are partially related, that is some portion of my sequence 1 is only related to some portion of my sequence 2. Okay, in that case, if sequences are partially related, then you are not advised to use cluster. Okay, and the final condition is that sequence that include short non-overlapping fragments are also not supposed to be used for alignment using cluster. There is a simple funda. If you give garbage in, the program will give garbage out. Okay, so if you give the wrong data, it would output the wrong data. So it is your responsibility to be a an effective user of any computer program that you are learning now and subsequently in your MSc as well as in your career. Okay, so each and every program that you use further in your career, each and every program is built on some premise. It is built on, say, some assumption, and it is your duty to find out on what assumptions that programs are built and what it can do and what it cannot do. So don't try to draw conclusions from the results you obtain from the program that is not mean to do the same task. Okay, so that is the user's responsibility.
Excuse me, sir.
हाँ बोलो बेटा.
Sir, Rajat wants to join.
Okay, okay, just a minute. Huh? Okay, so now this is whatever background that I required for beginning my discussion on tea coffee. I have already provided you with that. Okay, so now let us begin. Now you know what are the problems that are faced by progressive strategies. Okay, now we are going to study how this can be solved or how some of the problems can be solved using the subsequent algorithm that I am going to teach you. Okay, so the first algorithm that we are going to talk about is called as tea coffee, which is an abbreviation of a very big term like tree based consistency objective function for alignment evaluation. Well, that is quite mouthful. uh, okay, so now, well, just a kind of introduction to your tea coffee. Okay, I think Rajat has joined late, so this can be his last chance to uh, learn these things. Okay, so well, this Thomson et al. In 1994 proposed Clustal as heuristic approach for multiple sequence alignment. Well, as we have discussed so far, it suffers from greediness. It has got something called as the local minimum problem. Okay, so of these two normal problems that any progressive alignment strategy faces, tea coffee attempts to minimize that local minimum problem. And how it does that, I would demonstrate you in our subsequent theoretical lectures as such. Okay, so well, before we jump into what is this tea coffee and how do it work, well, let me tell you that what are the alternatives that are existing for well, so for example, for progressive strategies. Okay, what if I don't want to use this progressive strategy? Then what options do I have to align my sequences? Okay, so there are three alternatives that I will talk about. Okay, so the first alternative is you can use the simultaneous alignment of all of the sequences. Okay, so now there are two packages that rely on this approach, that is simultaneously try to align all of the sequences. Okay, so the two packages that perform such a type of task are this MSA that was developed by Lipman and his group back in 1989. Another one that was developed after 10 years, like in 1997, that software package was called as DCA. Okay, and both of these packages are based on this Carrillo Lipman algorithm. Okay, so now you can just imagine that you have got these huge number of sequences and you are trying to simultaneously solve the multiple sequence alignment problem. Okay, so that would eventually make your CPU and memory intensive task. ओके, तो अगर सब कुछ आप एक साथ में ही करना चाहते हैं तो उसके लिए सीपीयू भी ज़्यादा लगेगा, उसके लिए मेमोरी भी ज़्यादा लगेगी. ओके, एंड ऑफ कोर्स देयर इज नो गारंटी ऑफ फाइंडिंग द ऑप्टिमल solution. Okay, good. So the second alternative that you can explore is that you can use this iterative strategy. Okay, the iterative strategy was proposed by this group Goto et al. In 1996. Okay, so it is based on the concept of assigning weights to individual pair of sequences. Okay, so it uses the three-way algorithm to calculate and assign these weights that you are going to assign to individual pair of sequences. Okay, well, say for example, these sequences are arranged in MSA and again the weights are calculated. Okay, so what you begin with, say something called as the initial alignment. Okay, so in that initial alignment you assign some weight to those sequence pair. Okay, you can use this weight function, which we won't go into more detail of it. Okay, so now and you end up with your multiple sequence alignment, and then what you do is that you would again reiterate the same procedure of rearranging the sequences into your multiple sequence alignment and again giving some weight. Okay, and you would iterate this procedure till the point when there is no significant changes in the weights that has been calculated, and at that point you say that your alignment has been converged. Okay, so now the initial alignment that you begin with is generally created using progressive or simultaneous approach that I have discussed earlier. Okay, so this is second alternative. Okay, third alternative is that you can use both global as well as local alignment feature to be implemented in your multiple sequence alignment. तो इसके पहले whatever approaches that we have used, they were completely dependent on this global alignment approach for creating multiple sequence alignment. The alternative 3 that we are going to talk about, where this T coffee algorithm belongs, is that it uses the global alignment information as well as local alignment methodology for creating your multiple sequence alignment. Okay, so this local similarity can also be considered in MSA, and this is where your T coffee algorithm lies. Okay, it aims to use both global as well as local alignment feature in its algorithm. Okay, so well, let us now talk about what are the steps that are involved in your T coffee. Okay, so these are 4 simple steps. I'm going to go into detail of each and every step. So the very first step is that you would need to generate something called as a primary library. Okay, then you need to derive the weights for the so generated primary library. The next step would be you are supposed to extend the library, and finally you would be using progressive alignment for aligning the sequence. Okay, so in this way you would be using both the information from global and local alignment as well as features from progressive alignment strategies in order to deal with that local minimum problem. Okay, good. So let us talk about the very first step, that is how do we generate the primary library of an alignment, or what exactly is a primary library. Okay, so well, say for example you use two programs like clustr and align for generating this primary library. Okay, so well, say for example, since we are using both global as well as local alignment in our algorithm, तो global alignment करने के लिए we would be using cluster W, and for aligning the sequences locally we would be using la align. Okay, so la align would be used as a local pairwise alignment tool, and this la align is a component of this FASTA package. Okay, and this FASTA la align is, you can say, it is a FASTA implementation of another program called as SYN. Okay, so now once you have created a primary library using the information from global alignment as well as local alignment, what next thing that you are need to do is to assign weights to your primary library. Well, say for example, I would just demonstrate you with how weight assignment is done. Okay, well, say for example you are having four sequences: sequence A, sequence B, C and D. Okay, so first you would generate a primary library by aligning these sequences separately. Align sequence A and B, sequence A and C, sequence A and D. Okay, and a primary weight would be assigned to these sequences, or you can say these alignments. Okay, so now how weights are assigned? Okay, these weights are assigned based on the average identity among the match residues within the complete alignment. Okay, so if there is more identity during complete alignment, higher weight value would be given. If there is less identity during the complete alignment, okay, sorry, here should be lower weight value would be given. So in this way, these weights that you are going to assign to your alignment, they are not dependent on the coverage of your alignment, but they are dependent on how much identities you have obtained between two sequences. Well, say for example, consider these two sequences. Okay, now you can consider the sequence A or sequence B. These two sequences has been aligned, you know, इनका coverage ज़्यादा है because most of the sequence has been aligned, but still the primary weight given to this alignment is lower as compared to this particular alignment in which the coverage is smaller. राइट, यहाँ पर सीक्वेंस अलाइनमेंट का कवरेज कम है, राइट, बट स्टिल द प्राइमरी वेट इज हायर. ऐसा क्यों है? ऐसा इसलिए है बिकॉज यू नो द the you can say the identity in this alignment is less as compared to the identities that you have obtained in this alignment, the second alignment. यहाँ पर आइडेंटिटी मैक्सिमम है इसलिए प्राइमरी वेट इसका ज़्यादा है. यहाँ पर आइडेंटिटीज कम है, only half of the sequence has got higher identity, half has been left as it is, right? On the other hand, the entire second sequence has been added, you can say it is having maximum identity over here, therefore इसका weight ज़्यादा है. In this way you assign the primary weight to these sequences. ओके, इसे क्या कहते हैं अपन? वेट असाइनमेंट. ओके, नेक्स्ट व्हाट यू डू इज दैट you try to extend the so called created primary library. Okay, so now in the procedure of this extension, okay, you try to fit the third sequence between already aligned two sequences. Okay, so now if you want to extend the library of alignment of A and B through, well, say for example, you have got four sequences, right? A, B, C and D. So there are three possible alignments of sequence A and B that are shown over here. Okay, simple alignment of A and B, it has got some weight values. Okay, then you can align A and B through C. Again you can align sequence A and B through D. Okay, so what you have done here is that you have tried to insert the third sequence in between and then again calculate the weight based on what is the identity that you have observed while creating these alignments or these primary or secondary library. Okay, so again these weights are assigning after performing alignment through C or by adding another sequence D, and this procedure would be continued. Okay, so after the library extension procedure, you would end up with say some set of sequences. Okay, so now what you do, you would then proceed with a regular progressive alignment strategy. You have got sequence A and sequence B. Okay, so based on these sequences you would create a distance matrix between all the sequence. Okay, then based on the data from the distance matrix you would create a guide tree as we have done in your progressive alignment strategy. Okay, and whatever the two closest sequences are there as per your guide tree, you would align them using dynamic programming. Well, say for example, you can perform global alignment again using Needleman and Bunch algorithm. Okay, so while doing this progressive alignment strategy, you would consider the weight of the extended library. Whatever weights that you have obtained after extending the library, that you would be using while that information you would be using while proceeding further, for when you use this regular progressive alignment strategy for subsequent fourth step. Okay, now the thing is that the pair of sequence is then fixed and any gap that has been introduced cannot still be shifted later. Okay, तो अगर आपने फर्स्ट पेयर के बीच में अगर कोई गैप दे दी तो उसको बाद में आप शिफ्ट नहीं कर सकते आगे. ओके, then since you are using progressive strategy now, you can subsequently add remaining sequences according to guide tree. Okay, now the important fact here to be remembered is that you don't use any additional parameters such as gap penalties. Okay, यहाँ पर आप कोई gap penalties use नहीं करते. Why? Because you have already considered that factor when you were applying the weighing procedure. ओके, सो इसको अलग से गैप पेनल्टी देने की जरूरत नहीं पड़ती है एंड दिस इज वेयर योर लोकल मिनिमम प्रॉब्लम इज यूजुअली कंट्रोल. Okay, so in this way your tea coffee demonstrate that combination of local and global alignment can lead to significant increase in alignment accuracy. Okay, so now what you have done is that you have instead of using substitution matrix for aligning the sequences like PAM and Blossom, you have used some position specific scoring schemes, the information that you derived from your extended library. Okay, so this is how it differs from the typical or conventional progressive alignment strategy that you might have used in Clustal. Okay, so that is what all about your that was all about your tea coffee. So I hope you guys are now comfortable with the concept of using the local as well as global information for generating multiple sequence alignment, and how do we use it? What are the steps that are involved in your multiple sequence alignment using this tea coffee? Okay, well, now let us talk about our subsequent algorithm that is called as D-align. Ha, bol. Is there anything?
Sir,
Ha?
Shruti wants to join.
Oh, okay, there is no one. Okay, anyhow, I will be giving you this presentation as a recorded lecture. She can view it later. Okay, so the next algorithm that we are going to talk about is this dialign. This dialign stand for diagonal alignment. Okay, okay. So here are some key concept of this dialign or D-align. Okay, so this D-align is based on something called as segment to segment comparison instead of the conventionally used residue to residue comparison. तो इसमें आप क्या करेंगे, in whatever strategies that we have learned so far, progressive या iterative या simultaneous, either using global alignment or using global as well as local alignment, each and every strategy that we have learned so far, well, that completely used to depend on residue to residue comparison between the sequences that are involved. But this is an entirely new sequence, a different way of thinking, that instead of using residue to residue comparison, why don't we use segment to segment comparison? Okay, and the authors of this paper, well, they advocate that by using this concept, you can avoid the well known difficulties concerning the choice of appropriate gap penalties. Okay, so well, these authors say that they do not use any gap penalties in D-align, and how things are done, I would just try to explain you. Okay, so before we begin the concept of this D-align or segment to segment comparison, I would just like to refresh what is dot matrix method. Okay, so are you guys aware of this dot matrix method for aligning two sequences? Okay, anyhow, I will.
Yes, yes, sir.
Okay, so what do we do in dot matrix method? We align two sequence in horizontal and diagonal. Okay, and wherever there is similarity, okay, we would give points, right? ऐसे ही करते हैं ना अपन. So wherever there are similarities in your two sequences, you provide a dot. Okay, and then you try to figure out where are the diagonals, and this diagonal represent the similarity between these two sequence. You say that this much part of my sequence 1 is similar to this much part of my sequence 2, this much part of my sequence 1, this much part of my sequence 1 is again similar to this much part of my sequence 2. Okay, so that is how we do it. This diagonal somehow represent your alignment. Okay, so based on this concept, we are going to proceed further. Okay, so now here is a simple algorithm, is that you first need to define diagonals in your multiple sequence dot matrices. Okay, next thing that once you have defined the diagonals, you are supposed to weigh the significance of the diagonal. You have to perform assigning some weights. Okay, हर एक diagonal को आपको कुछ weight assign करना पड़ेगा, and then you would have to consider whether after weighing as well, whether the diagonal is significant or not. Okay, and the third step would be to compute the maximum alignment, and eventually what usually is displayed to you as a result is the so-called maximum alignment in this methodology. Okay, So here is how it begins. Okay, so we'll see, for example, you have these three sequences. This is sequence 1, this is sequence 2, this is sequence 3, and this is sequence 4. Okay, sorry, sequence 1. So what we are trying to do is that we are trying to align these three sequences: sequence 1, sequence 2, and sequence 3. Okay, so now the two sequences of all the sequences that we have here in this example, the two sequences are first compared in dot matrix. Okay, and you are supposed to figure out where are the diagonals that represent the similarity between the two sequences in question. Okay, so now similarly you do the same thing for remaining pairs of sequences as well. So this particular dot plot represent the comparison of sequence 2 and sequence 1, while this particular dot plot represent the comparison of sequence 1 with sequence 3. Okay, so whatever diagonals that you obtain in such multiple you can say comparisons, well, not all diagonals are considered in D-align. Okay, so क्यों सारे के सारे कंसिडर नहीं कर सकते? Why? Because these diagonals are not equivalent to each other. Okay, these diagonal represent the alignment of sequence 2 and 3, while these diagonal represent alignment of sequence 3 and sequence 1. These are not equivalent. These are, not one and the same. Okay, so what first you need to do is that you need to establish this consistent equivalence relationship among the so-called diagonals that are created in these dot matrices as such. Okay, so now a diagonal is said to be consistent when the overall order of the position of the diagonal in each sequence remain the same. Okay, someone is trying to join. Okay, हाँ, कहाँ पर थे अपन? हाँ. When we say that this diagonal follows the consistent equivalence relationship, when this when a particular diagonal or a set of diagonal, when they appear, the overall order of those diagonals, the overall position of those diagonals are found to be similar in most of the dot matrices that you have obtained. We consider only such diagonal to have consistent equivalence relation. ओके, तो ये हर एक डायगोनल अपन कंसिडर नहीं करेंगे. कौन से डायगोनल कंसिडर करेंगे? ओनली दोज डायगोनल्स दैट आर हैविंग दिस कंसिस्टेंट इक्विवेलेंस रिलेशन. Okay, and what is consistent equivalence relation? When the diagonal, when it appears, the order or the overall order as well as the overall position of the diagonals is similar in most of the plots that you have obtained. Well, such diagonals are said to be having consistent equivalence relation. Okay, so now once you have shortlisted those diagonals, okay, what you do is that you move on weighing the significance of each of the diagonal. Okay, so you are supposed to access the significance of each and every diagonal by weighing them. Okay, so now weighing would decide how similar or how dissimilar the two diagonals are. Okay, or whatever diagonals you have ended up with. Okay, and this enables effective selection of the set of diagonals. Okay, so the next step, what you do is that you try to assign some weight. Okay, over here a weight is decided, what we term it as WD. Okay, and it is calculated to access the biological relevance of the alignment. We'll say, for example, after assigning say some weight by say some procedure, if you end up having a high weight for a diagonal D, that would indicate that the similarity that is obtained throughout those multiple diagonals, that is not that do not happen just by mere chance. Okay, the highly weighting diagonals are supposed to be originating due to evolutionary processes that might be working in the background rather than just a chance movement. Okay, so that is why you need to weigh it and decide if it is significant or not. Okay, so once you do this, next what you do is that you try to compute the maximum alignment. तो ये हो गया individual diagonals के लिए. Okay, now we'll say for example there are multiple diagonals in this way that you would be considering. We'll say for example diagonal 1, diagonal 1, diagonal 2, diagonal 3, and there would be diagonal k. Okay, and all of these diagonal follow the consistence equivalence relationship. So what you do is that a score S is usually set that is obtained by adding the weight value of diagonal for first diagonal, and you go on adding till you reach the kth diagonal. क्यों? क्योंकि अपने पास में कितने diagonals है? We have got k number of diagonals. Okay, so now a consistent set of diagonals with maximum score are termed as maximum alignment. Okay, and whatever set that you have obtained with such maximum alignment score are reported as your results. Okay, so this is the basic concept behind your segment to segment approach of creating multiple sequence alignment. Okay, and here are some of the links that you might explore for using them practically. Okay, these two links, this one and this one, are for the server at which your D-Align and T-Coffee is hosted, and you can use this JAL view for, it is a Java based program. You can use it for visualization of your alignment. Okay, so this is what I have for you, at least for this session. And in our next session, we would be, I would try to demonstrate you how do we use these programs for your practical purpose. Okay, so now I am stopping this